My name is Martin Oates. I'd like to talk to you about using low-cost sensors based on Arduinos for collecting agrometeorological data. I'd like to cover two projects that we're currently working on. The first is looking at the possibilities for crop yield prediction using a low-cost sunlight analyzer and logger. And the second is looking at the automatic fault detection in a low-cost FDR-based soil moisture sensor. Okay, so the first of those presentations then is on the crop yield prediction system. Unexpected crop failure can be devastating, as I'm sure you're all aware, to communities and commercial growers. And this can lead to increased insurance premiums, volatile futures markets, overuse of fertilizers, pesticides, irrigation, a whole host of knock-on effects. Many yield predictions algorithms are based on NDVI estimates from satellites, but these can often be noisy due to cloud cover and a range of other effects. Growth models are often based on early stage crop development. For example, in corn or maize, there's the R1 silking phase, or there's the V6 or V12, the number of leaves on the early development crop. But these models are dependent on many factors, such as the soil type, the terrain, the climate, farming practices, meteorological data, etc., etc. And of course, as photosynthesis is critical to the growth, the quality of the sunlight is of particular importance. Photosynthesis is a multi-step process which makes use of different wavelengths of light, and the efficiency of that photosynthesis is improved in the presence of specific combinations of light, and this has been known for quite some time and is known as the enhancement effect. My understanding is that traditional solar radiation sensors can be quite expensive, and they usually give the brightness measure averaged over a broad spectrum of wavelengths. And this gives no real opportunity to analyse the specific lighting or weather conditions. What we're looking at here is the cost-efficient measurement over several wavelengths to try and determine a range of different sunlight conditions and try and then use that to optimise crop management resources. The main thing that we're going to use for this are LEDs. These are traditionally used as a source of illumination, but when they're exposed to light, they can actually produce a very small electrical current. When used in this manner, the LEDs present a range of interesting characteristics, such as capacitance, internal resistance, voltage saturation, etc., which make them non-trivial to use. However, we've looked at some of these challenges, and I think we've come up with some solutions which make them usable. This presentation is going to present some preliminary results from experiments with a 6-element LED-based sensor, and we're looking at different wavelengths of light from ultraviolet to near infrared. The sensor is able to distinguish between different lighting conditions such as dawn, dusk, moonlight, bright sunlight, and different types of cloud. And the sensor costs about €10 to produce, and that includes its box, its batteries, and its radio transceiver. The key to getting them to work is having 11 time-spaced light readings, and these are taken on each of the channels. That's infrared, red, green, blue, ultraviolet, and a red one with a filter, although we actually end up not really using the data from that. Before starting reading the voltage generated on each channel, the analog input is configured as a digital output and set to 0. What this basically does is it makes sure it discharges any current and voltage that's in the input path. We then take 4 readings in immediate succession with the processor interrupts turned off. This is to try and get 4 very quick readings. As the Arduino is capable of delivering several thousand readings per second. Those 4 readings are all taken in considerably less than 1 millisecond. We then apply incremental delays of a further 1 millisecond and 2 millisecond before taking the 5th and 6th readings. Then a further 7 milliseconds, and we switch off the interrupts, switch back on the interrupts so that the processor can act as normal and take the 7th reading. The reason the interrupts are turned off is basically to ensure that those timings are as accurate as possible. We then apply incremental delays of 20, 70, 200 and 700 milliseconds to get the 8th, 9th, 10th and 11th readings. So we've got a series of 4 readings taken very quickly, then a reading taken nominally at 1 millisecond, 3 milliseconds, 10 milliseconds, 30 milliseconds, 100 milliseconds, all the way up to 1 second exposure time. Okay, so that's the group of 4 and then 7 further readings spaced out over exponential times. After all 11 readings are taken, the results are transmitted or logged as required. So if we look at typical readings under direct sunlight, here are our 11 readings, these 4 taken in quick succession, and these are the ones over the exponential time frame. You can see that the infrared reading, and this here, I believe is in, yeah, this reading here, you can see it's saturated straight away. This reading remains high for all 11 readings. If we look at this in contrast with the red filtered LED, you can see we get near linear growth over those first 4 linear time-spaced readings, and then we get the saturation. By contrast, if we look at these readings taken at dusk, when obviously the light levels are much lower, you can now see that our infrared readings now grow quite slowly and then saturate at a much lower level than they did on the previous slide. And what we basically said was, right, how can we take a subset of these values and try and use this to say what are the current lighting conditions? So instead of looking at all 11 of these, we look at the 1st, the 4th, the 7th and the 11th, and we don't even bother with the red filtered light at all. Okay, so here then was a summary under different conditions. This was direct sun, bright blue sky, etc., different types of cloud, and you can see our reading 1st, 4th, 7th and 11th reading, and these now are a percentage of the largest reading ever seen for that particular type of LED. Just cuts the data down to more manageable levels. So you can see here that under direct sunlight, the infrared one saturated straight away, and there we just got a little bit of noise. Here the ultraviolet channel built up slowly. We now fed a selection of these values into a classifier system. This was developed by John Holland many years ago and tends to use what are called evolutionary computing techniques. But basically we fed those into the classifier system, which was allowed to develop a rule set and then characterize what type of conditions it thought it had seen. And here's an example of one of the rule sets that we used. So for example, if the infrared 1 reading was greater than 50, we simply say it's direct sun. If it's not that, then if the red level is less than 20, we go to the dark part and we follow this. So basically it just generates an algorithm for us. If we look at the output now over a typical day, you can see that early in the morning there was no moon, then there was some light pollution, dawn, poor sky, blue sky, direct sun as you might expect here. Here there was some haze that must have come along around about 11 o'clock, more direct sun, and then shade in the afternoon. And that shade actually is a bit of a bugbear that we'll come on to later. If we look at this graphically over a typical day, well, I've only shown 20 hours here because the last 4 hours aren't of interest. Basically you can see that these 2 lines here are the red and infrared readings with the 1 second exposure time. So as soon as you get any daylight whatsoever, these channels saturate. But what's interesting is that at night they can be used to pick up either light pollution or the moon, and we'll see that in a moment. By contrast, if we look at the infrared and red ones taken with only 0.1 millisecond exposure time, so this is the R1 and the IR1, we see basically values that rise here. We get differences between the red and the infrared, and in the afternoon, unfortunately, these levels drop. And that's because the sensor then entered the shade of a nearby building. And that messes up some of the results later on, unfortunately. What is also interesting though is that the level of ultraviolet light that we measured, or one of the measures, was a fairly gentle curve up and down during the day, showing that in general the level of cloud doesn't interfere with the amount of ultraviolet that's reaching the ground. If we look at that over a 32-day period, and this was some particularly interesting data because it started with fairly stormy conditions that lasted 3 or 4 days here, and you can see that during that time basically we didn't get any real bright sunlight, and the cloud level at night was actually meaning that the sensor was spotting that cloud rather than saying it's nighttime. Here we're seeing at night time a pickup in the level of infrared light, and that is actually detecting the full moon that occurred here. So we're seeing the waxing and the waning of that moon, and you'll see that in a moment. The top trace here is a numerical representation of the classifier output. So at the bottom here, obviously you've got very dark conditions. Here you've got the fact that it thought it was moonlight. Here you've got the fact that it thought it was direct sun, and obviously you've got no direct sun during that period. And again, the amount of direct sun on each of those days. I didn't have access to a pyranometer or other device for correlating this, so what I did do was I took the maximum temperature and the daytime average temperature from an independent data source, and I tried to correlate that against the number of minutes of direct sun that the sensor saw. And I've also plotted the number of minutes of moonlight just for interest. And you can see here that this is the number of minutes of direct sun, and there is clearly a positive correlation between the number of those minutes and the daytime average and the maximum temperatures. You can also clearly see that full moon period which occurred here. Yeah, so basically you can see there's a correlation, and if we plot that on an XY trace, you can see down here were the days where the average temperature was low and the number of minutes of recorded direct sun were low. Here you're seeing higher temperatures and more minutes of direct sun. These 5 outriders occurred here where we had the maximum temperatures, and unfortunately because the unit was going into the shade of a building, it could only record so many minutes worth of sun. In the afternoon it couldn't see the direct sun in the afternoon. So really these 5 readings were probably over here, much further over. I couldn't speculate as to what those precise number of minutes were, so what I did was I capped these values down to 22 degrees and reran the correlation, and that improved the correlation factor from 0.66 to 0.77. Okay, so in conclusion, I think we can see that we can clearly demonstrate the sunlight analyzer can classify a wide range of sunlight conditions. In this example we used direct sun through hazy cloud, poor light and moonlight, and it did correctly identify the full moon where cloud conditions allowed. And some research has shown that moonlight can be particularly important for certain pollinators, for example, in certain types of crops. Whilst it wasn't possible to correlate the classification of the analyzer with the output of a similar device, it's been demonstrated that the classifier output for the sun gives us a correlation in excess of 77% when we look at the recorded daytime average temperatures. Using this information, the sensor could be programmed to use the Arduino outputs for real-time control of other crop management resources such as irrigation, artificial illumination, heating, shade, pest management or pollinator support. Or alternatively, the information could be passed on to another management system. A larger field trial for this analyzer is proposed, where we can cross-check the results across several devices and comparing the results for those with a commercial solar radiometer, for example, some sort of pyrometer. And if that's successful, what I'd like to do is to co-locate some of these units in an area where they're actually going to do some yield prediction information. Obviously that will take a longer time scale, and we can see whether or not this device is in fact useful. Okay, so that was the first project I want to talk about. The second one is automatically detecting faults in a low-cost FDR sensor. As I'm sure you're all aware, there's a wide range of electrically based soil measurement techniques, such as resistive methods such as Wenner arrays, Schlumberger arrays, capacitive methods such as FDR and TDR, as well as radiation-based techniques such as the neutron probe. Whilst low-cost implementations of the resistive sensors have been suggested in the past, commercial implications tend not to be that low cost or simply aren't available. The principal operation of the FDR capacitance probe relies on the fact that the capacitance of the probe is highly influenced by the dielectric constant of whatever is between the plates. The difference in that dielectric constant between water and air is about a factor of 80, so there's a possibility for significant differences here. And the presence of water between those plates produces a highly significant change in the probe capacitance. This capacitance can then be measured by electrical means, and as the probe is insulated, there is no direct current flow within the soil, which reduces any influence of any conductive ions within the soil. This is the part of the circuit of the probe electronics. Here the probe is represented by this capacitor, and it's fed by a signal generated here on input D3. And in this first technique, we use the probe as the capacitive component of a low-pass filter. So those of you with an electronics background will recommend a classic RC arrangement. We pass a signal into the probe at a fixed frequency. We've used 250 kilohertz and 125, 83 and 62 kilohertz and recorded the values that we got through. Basically this is then passed on to a zero unity gain amplifier stage to impedance match these two components. We then pass this on to a peak detection circuit so that the analog voltage that's read here gives you some idea of how much was reflected by the filter system. The values here are recorded using a 10-bit analog to digital converter, but we then rescale those to a 0 between 0 and 255 for ease of storage and transmission. Microseconds after doing that result, basically we now use the probe in a different way. This capacitor is now the controlling element of this oscillator. Basically this capacitor is charged, which changes the threshold level of this detector, which then switches it into discharge mode, etc., and the cycle just repeats so that this circuit now oscillates. The time it takes that capacitor to charge is measured, both the charge and the discharge time, on this pin of the microcontroller. A unit with a single probe can be built for less than 10 euros, and again that includes the temperature sensors that are needed, the IP56 box, the batteries and the transceiver. There is a modification to the system which will allow up to 4 probes on the sensor, and that pushes the cost up a little bit. This is an example of one of the probes that we've been using. It's a PCB about 60 millimeters by 20 millimeters. You can see it's a double-sided thing with 2 parallel prongs. Those prongs come out to electrical connections here and here. And basically the whole of that PCB assembly is dipped in varnish, which is allowed 24 hours to dry before a second coating. However, as we soon found out, the insulation on these probes and the wiring for them are subject to damage. And further, it's possible for moisture to enter the electronics themselves, both of which can affect the results. And we wanted to be able to detect that because we didn't want an incorrect value. If we look at the signal strength readings that we got using the 4 different frequencies we've mentioned, so this one here, for example, is the 62 kilohertz, 83, 125 and 250 kilohertz, you can see that these signals drop when, instead of the probe, we put a known capacitance as the input to the device. So you can see that as the capacitance increases, so this value drops. In contrast, as you would expect, as the capacitance increases, the time to charge and the time to discharge increase linearly. But to make those values useful, basically we looked at the reciprocal of the signal strength and scaled it by 8,000. We now end up with a whole load of straight lines. However, as you can see, the 250 kilohertz line is tending to do this, and the 62 2 kilohertz line is tending to do this. So we're not getting very good straight lines here and here, but the middle ones are quite straight. What we are seeing, however, is that there's a clear now linear relationship between the capacitance and the signal strength, and the capacitance and the time to charge or discharge. And hence you would expect there to be a linear relationship between the signal strength and the times. If we look at that situation, we've now got the time to discharge the capacitor and the time to charge the capacitor. And if we do a linear regression analysis on these, we will see that we can produce a slope of about 1.75 with an intercept of 12.2. What I've also shown here is the same values if that intercept is changed to 17, and you'll see why I've done that in a moment. If you note now that all these numbers here are falling roughly in the range 1.75 to 2.05, that range is important. If we now look at the results when we put the probe into soil under a whole range of different moisture conditions, now you can see that we get a slope of 1.99 with an intercept at 21.5. And what I did was I took the 21.5 from this and the 12.2 from this and produced an average of 17. So that we now have a metric which we can use on both the capacitors and the soil. And you can now see that again, all these values are in this magic range of 1.75 to 2.05, an important range. Now to simulate damage to that sensor, we went back to the capacitors and we put a resistor in parallel with them. So this represents a scratch or some form of damage to that sensor. You can now see that when we just had the cable connected, these are the values for the reciprocal signal strength, the time to discharge, the time to charge, and again our number here is in our magic range of 1.75 to 205. But as soon as we put a resistor here of 4 meg 7, and as those of you will know that's quite a large value of resistance, our values have strayed outside that magical range. This is greater than 205, and indeed as we made the resistor smaller and smaller and smaller, that value got larger and larger until we got to a point where the oscillator would no longer oscillate. These 499 values are a timeout value. I mean, the circuit was not oscillating. If we take that example of the 4 meg 7 resistor and look at all the capacitor values we tried, you can see that in all cases we have exceeded our 205 limit on this metric that we've devised. So it's not unique just to that one capacitance. So we then did a 6-day trial in real soil, and you can see here the temperature of the soil, which varied between 20 and 45 degrees on each of the 6 days. This is the temperature of the box electronics, which actually turns out to be important for correcting values. That varied between 20 and 35 degrees. And here is our trace of this metric we've developed, TC plus 17 divided by TD, which for all cases, even as we traversed the 2 irrigation events, you can clearly see still remained within this magic range of 1.75 to 205. So it's showing that that metric is telling us the sensor is still okay despite a wide range of temperatures and a wide range of moisture levels. These are our first 4 days of drying, so these are our signal strength values and our time to discharge values over those first 4 days. Here's the first irrigation event, here's the second irrigation event. What we also see is that this signal strength technique, the blue line, is obviously more sensitive in wetter conditions than our time to discharge method. So in conclusion, by utilising 2 different capacitive measurement techniques on the same probe, one based on a fixed frequency and the other on a variable frequency, we can see a distinction of experimental conditions. We could tell the difference between the capacitors and between the soil. And what I'm hoping is that as we try it in different types of soil, we may well be able to get some indication of the properties of that soil type. In terms of raw resolution, the fixed frequency signal strength technique is theoretically more sensitive to linear changes at lower capacitance values, i.e. dry soil conditions. However, when it's turned into its reciprocal value, what we actually find out is that technique appears more sensitive under wet soil conditions, as you saw on the last slide. And by looking at the ratio of the time to charge and the time to discharge, the TC and the TD values, we develop the metric which can be used to determine if the sensor has been affected by either damage or condensation, regardless of the temperature of the soil or the box electronics or the moisture level within the box. This is true even though the readings themselves appear to be within normal ranges, and obviously this is essential to avoid incorrect or inappropriate irrigation and can be used to allow the sensor to transmit a known error condition. Hopefully once we've perfected this sensor, it'll be highly suitable for large-scale agronomic deployment where large numbers of plants need to be individually managed at low cost. I'd like to express my thanks to Telinatura and to UMH for their assistance with the work we've done on this. Thank you very much. Any questions?
I have a question.
Uh-huh.
With all the components that are you using, do you think that if we use a better components, more expensive, it's possible to obtain a better signal?
I believe so. I mean, at the moment, the drive has been for absolute minimum cost. Okay. There may come a point where we turn around and say, no, it's worth spending 3 times as much on that particular component to get better results. Yes.
I think that is not good a hyper low cost sensor because we will lose a lot of signal, and I think that we have to adjust, or you have to adjust. Yeah. With better components.
I think you're quite right. What we're trying to do is strike a balance between something which can be mass deployed on maybe a 1 per tree basis in an orchard to control irrigation, as opposed to a scientific instrument. There is obviously a trade-off between those two. Jörg?
Have you tested the influence of the salinity in the when you are taking data
Yeah.
of this kind of sensor?
Yeah.
The salinity has, I think, an important influence.
It does, yes, you're quite right. We've got other experiments that we've run with salinity and at different temperatures, but there was a limit to what I could show in 25 minutes. Okay, any other questions? Thank you very much.